Hi everyone. We left off the other day with the idea of isotopes. So remember, isotopes have different numbers of neutrons, but they have the same number of protons. So why on earth do we consider these atoms that have different numbers of neutrons to be the same element? If you remember from last time, we kind of covered this idea that despite these numbers of different neutrons, which are neutral, the isotopes are going to be chemically alike. They have identical numbers of protons and electrons. It is the protons and electrons that actually do all of the chemical behaviors. So if something is going to be reacting with one another, it depends on the number of protons and electrons, not our neutrons. So we have looked at how the idea of protons, neutrons, and electrons are similar. However, we haven't actually looked at the mass. So the mass of even the largest atom out there is extremely small. Since the 20s, it's been possible to determine the tiniest amount of masses by something called mass spectrometry, which this you will not need to know for test. Just wanted to let you know how we figured this out. And we found out that the mass of something with the atomic number of 9, which is fluorine, was found to be 3.155 times 10 to the negative 23rd grams. So just for a frame of reference, something like 58,000 grams. So that is a humongous difference. So atoms are extremely small. Now, whenever we're looking at isotopes, we actually found that we needed some way to unify all of the masses that we were looking at because they're so small. So we came up with the idea of the atomic mass unit, or AMU, and this is the number that you're going to see in the periodic table. You will see something like this, where you have the atomic number up at the top left-hand corner, the symbol, and then you would see the atomic mass unit down at the bottom. That's this guy at the bottom. So to figure that number out, we have to look at the mixture of two or more isotopes, because isotopes occur naturally in the atmosphere, and they have a fixed mass and a natural percent abundance. Okay, so we're going to use the mass of each of these different isotopes and how often they occur to determine the atomic mass of each of these elements on our periodic table. So here's a couple examples of all of the different types of elements that have different isotopes. So for example, we have hydrogen 1, which is very abundant. You have 99.985% of all the hydrogens that you're ever going to find being the hydrogen with a mass of 1.0078. We then have a different kind, which is a very, very small amount, which is 0.015%. So of all of the hydrogens that you're finding in the whole entire world, 0.015% of them have a mass of 2.0141. There is another type of hydrogen that is out there, but it's so small that we completely ignore it. And it has a mass of 3.01360. Now, when you calculate the different atomic masses, you are going to notice that whatever answer you get, or whatever atomic mass you get, will have a number similar to the most abundant isotope. So for example, if we look back at our hydrogen, our atomic mass, after doing some calculations, is very similar to the most common isotope in the atmosphere. That isn't surprising because you want that number to reflect the most common type of isotope. So to determine the atomic mass, we're going to take a look at the following. Okay, so I've copied this down from the previous slide. We have two of our isotopes for carbon here on the left. And you can see that this one is carbon 12, meaning that the mass number is 12 and the atomic number is 6. And then we have the other isotope carbon 13, which has a mass number of 13 and the same number or the same atomic number as the previous isotope. We also have our percent abundance. So carbon 12 is way more popular than that of carbon 13. And the masses of each one of these has also been recorded. Now to determine the atomic mass, you need the following equation. So to find the atomic mass, you need the mass of your first isotope times the percent abundance of your first isotope. And all of the time you have these percent abundances, they need to be written as a decimal. So that means you're going to divide by 100. Then you're going to add that to the mass of your second isotope times the percent abundance of your second isotope, again being represented as a decimal. That's important. So for this example, we have carbon 12, which it has a mass of 12.000 times the percent abundance of 98.89, which is 0.9889. That all represents carbon 12 isotope. Then we're going to add that to carbon 13, which is 13.003 times the percent abundance as a decimal, which would be 0.0111. And this all represents carbon 13. And if there were more isotopes, we would continue to do the same thing for all of your isotopes. Go ahead and put that in your calculator and you should get a number like 12.011. You may get something a little different based on how you rounded. However, look at the number itself. It most closely resembles the number that is most popular. The number that is most popular is our carbon 12 because that's 98.89% of all the carbons you're ever going to find. And that is taken into consideration by doing this calculation. So overall, you're able to take the natural abundance and the mass of each of your isotopes to find the atomic mass that's on your periodic table. Here, this takes you through another one for chlorine. So you have two isotopes, chlorine 35 and chlorine 37. And remember, the 37 and the 35, those are your mass numbers. So they go in your superscript position. If you calculate the arithmetic mean, so like you would normally do averages, you would get something like 35.98. However, that's way higher than the actual value. So to explain this away, remember we're taking the weighted average, meaning that we want to take into consideration which one is most popular in our atmosphere. Since we have a whole lot more of chlorine 35, we want an average that better represents that number. So if we were to take the average atomic mass, remember this is weighted like we did before, we would take the atomic mass of number 1 times the percent abundance plus the atomic mass of number 2 times the percent abundance. So for example, according to the last slide, we have our carbon. So again, if you take that weighted atomic mass, you would take the mass of the first isotope times its percent abundance as a decimal and add it to your second mass times your second percent abundance as a decimal. And you're going to get an answer close to 35.435. And that number better represents the average mass of what you're going to find in a population. So just in case you need a written out definition, the atomic mass of an element is the weighted average mass of the atoms naturally occurring. So if you want to look at that again, that is the mass of your first isotope times your percent abundance plus the mass of your second isotope times your percent abundance of that isotope. Oops, I forgot the D. So when you have this mass times your percent abundance, it's going to reflect both the mass and how often they occur. That's very important, and you will have to put this on the test. This is a great test question. So if you were to look at the atomic mass of copper, which is 63.546, which of the two is more abundant? Copper 63 and copper 65. Remember that this weighted average is going to reflect the mass of the most common element and how often it occurs, so the abundance. So since we have something that is close to the number 63, my best guess is that the most abundant element would have to be copper 63. So if you were to look through the steps, remember the atomic element or the atomic mass of an element is going to show the mass and something that is naturally occurring. Since you have something closer to 63, that's most likely going to be the one that is the most abundant. And that idea is taken through here as well. Here's another example of how to go through and calculate the atomic mass. Again, if you are going to do this, you need three things. You need the number of stable isotopes, the mass of each one, and the natural percent abundance. So if we were to look at carbon, it has two stable isotopes, and we've actually already done this example. So if you would like to try it again at this time, feel free. So here is one for calculating the atomic mass of an unknown element. It has two naturally occurring isotopes, one with a mass of 10.012 AMU, and it occurs that often, and another one with 11.009 AMU with that percent abundance. So let's try and figure out the atomic mass of element X. Okay, so I translated the information from the last slide onto this one. So remember, our atomic mass is the mass of the first one times the abundance of the first as a decimal, plus the mass of the second times the abundance of the second. So let's go ahead and plug in those values, and you should get a layout similar to this. Again, this first section is for the isotope number 1, and our second section is for isotope number 2. Now go ahead and plug these into your calculators, and you should get a number similar to 10.810. And if you want to take this through again a little clearer, you can look at the notes that we have in the PowerPoint as well. It takes you through the same exact steps and maybe a little bit neater fashion. And as always, we have this great information at the end of the PowerPoint just to summarize what all we've covered. All right, I will see you tomorrow.